Alright guys, so this is lesson 5. We're going to talk about something called end behavior today. Clear that stuff off. Alright, so we're going to learn what end behavior is, and also I'm going to introduce you guys to something for calculus. It's not calculus, but it's a topic that prepares you for calculus, known as limits. I'm going to introduce you guys to something called limit notation. So here we go. You don't need to write this. I would like you guys just to watch. So suppose that I have this function here, y equals 2x plus 1, and I've got these x values, okay? So if I were to plug in 1.2 for x, that's a weird number to plug in, but I'm going to go ahead and do that. I would get 3.4. So let's plot that point. 1.2 would probably be like right about here, and my 3.4 would probably be like right about here. So I've got a dot here, right? Get rid of that. Okay, let's continue that process. Let me know, how about 1.4? 1.4 and 3.8. So 1.4 is going to be like here, 3.8 will be like right about here-ish. And I'm just going to continue the process. 4.2, if I plug in 1.6, I get 4.2. 1.8 would give me 4.6. As you're wondering what's the point of this, you'll see in a minute. 1.9 gives me 4.8. And as you guys can see, what's happening is these dots are moving in this direction, right? So I'll turn these dots into arrows. And we're approaching something there, aren't we? What are we approaching? So let's take a look at this. As x approaches blank, y approaches blank. So let's take a look at our x's. My x is going from 1.2 to 1.4 to 1.6 to 1.8 to 1.9. What x value am I getting closer and closer to here? What x value? Well, x is approaching 2, right? Now, as x is approaching 2, as I approach x equals 2, what y value am I approaching? The y value I'm approaching would be, you have to look at the graph to tell this one, or I guess you could look at the table too. The y value is getting closer and closer to a y value of 5. Okay? Now, you might think that's stupid, and I understand why. Because you're thinking, if I wanted to know what y was when x equals 2, I would have just plugged in 2 and gotten 5. And you're right. But the point is, I'm not talking about plugging in 2 and getting 5. I'm talking about approaching 2, getting closer and closer to 2, causes the y value to approach 5. So we're talking about approaching something, okay? And that is the concept in mathematics known as a limit. Now, it may seem stupid for this function, but for other functions, it's not. So here is the proper way to do notation for limits, okay? So I'm taking the limit of a function, okay? That means we're approaching something. And here's where we put the x's. This tells us what our x is approaching. X is approaching some number. We'll call it c in this case. As the function x value approaches c, the y value, that's the y value here, approaches L. So that's limit notation. So if I wanted to apply this to the last problem we just did, I would do this. We were taking the limit of the function 2x plus 1 as x was approaching 2. So the limit of that function as x approached 2 was what y value? 5. That's limit notation. May seem a little bit silly, but remember, the point is that we are approaching something. Now, why is this not silly? Well, in calculus, you'll find that there's actually situations where you can approach something, but you can't ever actually get there. And actually, in this class, we've talked about such things too. What about asymptotes? You guys remember asymptotes? Like, let's say I had a vertical asymptote here. You can approach an asymptote, but you can't actually ever reach it. Okay? So that's an example of mathematics where yes, you can approach something, but you can't actually get there. So in this case, the point of a limit is talking about what you're approaching rather than talking about what you are. Okay? So that's the point of a limit. And calculus is completely based on this topic. This topic is the heart of all calculus. You won't know why today, obviously, but if you take calculus in the future, you'll know why. Limits are the heart of all calculus. Anyway, so now I'm going to talk about something new, and it's connected to these limits that we just talked about, but let's switch gears for a minute. We're going to talk about something called end behavior. Okay? And what that means is it's talking about what's happening at the ends of your function. Okay? So like take this function for instance. I'm going to just draw a function here. Well, at the ends of this function I've got some arrows, right? What's happening at the ends of these functions? Well, on the left end, it's going up. And on the right end, it's going down. That's what we call end behavior. Okay? Now, I guess I'll go ahead and take this opportunity to try to connect it to the idea of limits for you a little bit. Okay? So let's say that this function's called f of x. All right? We want to find out what is this function approaching. So we're talking about a limit, right? We're talking about approaching something. So that's a limit. As x goes to something. Now, x is about going left and right. So in this case, I'm going to the left, and arrows mean forever. So x is approaching negative infinity on the left side. So x is going up to negative infinity. What is the y value approaching? Well, the y value is going up. And up means infinity. It's a lot like the domain and range thing that we talked about. So the limit of this function as x goes to negative infinity is positive infinity. Another way of saying this is as x goes to the left, y goes up. Okay. On this side over here, what's my function approaching? Now, by the way, you might be wondering, why do we use limits for this? You can't ever reach infinity. You can only approach it. And so that's why limits are relevant here. You can't reach infinity. You can't say your function equals infinity. You can only say it approaches infinity. So the limit of this function as x approaches infinity, meaning I'm moving to the right now. That as x goes to infinity, that means I'm moving to the right. What's the y value doing? Well, the y value is going down, so that would be negative infinity for this particular function. So this is limit notation that's describing the end behavior. Okay? So that ties those two concepts together for you. So let's talk about a couple of functions here. I don't think I printed these for you. You don't really need to write this, but I would definitely watch it and understand it because it'll help the other things we're going to do later in the block make more sense. So here's our question at the top. What is the end behavior of these equations? And what we're going to do is we're going to write it in limit notation. Okay, so first of all, y equals x squared. I'm going to explain this to you guys in two ways. I'm going to explain it with a table and with graphs. Okay, so let's start with a table. I want to know what's the end behavior. That means I want to know what's happening as x goes to infinity and as x goes to negative infinity. Okay, so let's start with going to infinity. So like let's start by plugging in 1. If I plug in 1, what do I get? I get 1. What do I get if I plug in 10? If I plug in 10, I get 100. What do I get if I plug in 100? 100 squared would be about 10,000. So let me ask you guys this. As x is getting bigger and bigger and bigger, in other words, as it's approaching infinity, what's the y value doing? The y value is getting bigger and bigger and bigger. In fact, it's getting bigger much faster than the x's are. So y is also going to infinity. So the end behavior of this is that as x approaches infinity for this particular function, x squared, the y value is infinity. What about as we approach negative infinity? So let's start with 0. If I plug in 0, what do I get? I get 0, right? What if I plug in negative 1, though? Because I want to start approaching negative infinity, so I've got to work backwards. If I plug in negative 1, what's negative 1 squared? Well, that's a positive 1. What if I plug in a negative 10? It's going to be a positive 100. What if I plug in negative 100? That's going to be a positive 10,000. See, what happens is the square is canceling the negative every time and making it positive. So let's think about this. As x starts at 0 and gets closer and closer to negative infinity, what's the y value approaching? The y value is not getting negative. What's it becoming? It's becoming positive infinity. So the limit of this function as x approaches infinity is, I'm sorry, not infinity, negative infinity, results in a positive infinity. So that's the table way of understanding it. Now I want to show you guys the graph way of understanding this as well, because they kind of go hand in hand. Hi, Bailey. Hey, buddy. Hi, Bailey. All right. So, what does this graph look like? Mr. Bailey. So this is a quadratic, right? You guys know what they look like. They look like this. So here's the graph way of looking at it. As I move to the left, negative infinity, the y value goes up, positive infinity. Or as I move to the right, the y value also goes up. Okay? I don't think I'm going to do the table thing for the rest of these. For the rest of these, I'm just going to do graphs. Okay? So let's take a look at the next one here. Now, you guys know what this one looks like. Negative x squared is going to be upside down. So see if you guys can help me out here. What is the limit of this function? I guess I'll put negative x squared. What's the limit of negative x squared as x approaches negative infinity? Now, remember, that means I'm going to the left. So as I go to the left, what's the limit? What's the y value approaching? Well, it's going down, right? So that would be negative infinity. I would challenge you guys to see if you can figure out what this would be before I say it. What is the limit as we approach positive infinity? Well, positive infinity means I'm moving right. It's still going down. So here's what I want you guys to notice about this slide here, is that for both functions, since we had an even exponent, over here both sides went up. Over here, an even exponent with a negative coefficient, both sides went down. Okay? So that's kind of the big takeaway there. Now, let's go ahead and change it up a little bit. Now, x cubed. We could do a table again, but I'm not going to. If we did a graph, it would look like this. That's what x cubed looks like. Those of you guys who did the extra credit, you might remember that. Now over here, this is negative x cubed. Negative x cubed looks like this. So, what is this function approaching as x approaches negative infinity? The answer is negative infinity. As x moves to the left, y goes down. How about as x approaches positive infinity? Y goes up. So notice this time, notice how they're opposites? On a parabola, they both went up. But on a cubic function, one goes down, one goes up. Over here, as we move to the left, what's happening? As x approaches negative infinity, the y value goes up. And as the function approaches positive infinity, the function goes down. So here's the big takeaway I want you guys to have from this one. Okay? When the powers are odd, the ends go in opposite directions. In this case, it went up on the right and down on the left, right? But when it was negative, the left went up, the right went down. Okay? So odd powers make the ends go in opposite directions, whereas even powers make the ends go in the same direction. Okay? So that's your big takeaway that I want you guys to have, and I think we're going to summarize that in a table here. This is a table I definitely want you guys to write down, and if you don't have it, then you're going to be sad for the rest of the day. You need this. So go ahead and pause the video here and copy down the table. All right, so here's what we're going to put in our table. When you have an even exponent and a positive coefficient, like x squared, it goes up on both ends. And the way that we describe that with limit notation looks like this. That's left. I should have a negative there, sorry. And that's what happens on the right. They both go up. Okay? And if I put a negative in front of my x squared, like that, right? It flips the parabola upside down, right? And so the left side and the right side go down. So the limit as x approaches negative infinity is negative infinity. And the limit as x approaches positive infinity is negative infinity as well. Okay. When you have an odd exponent, like x cubed, the ends go in the opposite direction. So in this case, when the coefficient was positive, it went up on the right and down on the left. So the limit as x approached negative infinity was negative infinity. But the limit as x approached positive infinity was positive infinity. But if we put a negative in front of that x cubed, it flips it upside down, and so that causes the left side to go up and the right side to go down, and we have this. The left side goes up to positive infinity, the right side goes down. Okay? So on your test, you're going to know two things. Based on the exponents and coefficients, whether the exponents are even or odd, and whether the coefficients are positive or negative, you should be able to draw arrows for me to tell me which way the ends of the graph are going. What's the end behavior? Second of all, I would expect you guys to be able to use this limit notation as well to describe what's going on. Okay? So, that's two expectations I would have from you. Now we're going to go ahead and actually do some problems here now to kind of put your stuff to work. So, what can you conclude about the end behavior of this function? Now it says, don't copy this, it'll take too long. You guys have examples on your notes anyway, and we'll get to those in a minute. But for now, let's go ahead and just work it out. So, first of all, I want you guys to notice this. I've got an even power and a negative coefficient. Look at your charts. What do your arrows look like when you have a negative coefficient and an even power? When you have a negative coefficient and even power, it's going down on the left and it's going down on the right. That's your end behavior. But I also want you guys to be able to describe that using limit notation. The function goes here, so we'll put 5x to the fourth here. X approaches something, and y approaches something. You have two blanks to fill in. Here I'm moving to the left, so that would be negative infinity. And it's going down, so that would be negative infinity as well. The limit notation for this one would be I'm going to the right, so that's positive infinity, but the y value is still decreasing, going downwards, so that would be negative infinity. So this is the two things I would like you to do. Draw the arrows and describe it using limit notation. All right, let's go ahead and take a look at, if you want, I'll leave that up there in case you're still writing. What can you conclude about the equation here? All right, in this case, we're not going to write limit notation or anything. Instead, I just want to know, what can you know about the equation? In other words, what do we know about the coefficient? And what do we know about the exponent? So notice it goes up on the right and down on the left. Now look at your chart. Which one goes up on the right, down on the left? And what does that therefore tell us about the coefficient and exponent of this function? When you're going up on the right and down on the left, they're going opposite directions, right? So I know my exponent must be some odd number. And since it's up on the right, down on the left, that means it must be a positive coefficient. So for instance, if you were to graph, if the equation of this could possibly be something like 4x to the third, technically. Okay. I mean, it may or may not be, but it could be. So that's that. So here's a student practice. I want you guys to pause the video and see if you can answer these two questions in the same way I just answered the last one. And I will put the answers up in just a moment. Okay, so here's your answers. Down on the left, up on the right. The limit as x goes to the left is negative infinity. The limit as x goes to the right is positive infinity. Over here, they're both going the same way, so we know that the exponent's even, and they're both going down, so we know that's negative. Okay, let's continue our discussion here. So now we're going to talk about something else. I'm going to talk about the battle of the terms. So in this corner over here we have 10x. And in this corner over here we have x to the fourth. And they're going to go at it. We're going to start off with round one. So I'm going to put a 1 here for round one. How we can tell which one's the winners, we're going to plug in 1 and see what we get. So if I plug 1 in over here, I get 10. But if I plug in 1 here, I get 1. So 10x wins round 1. Let's go to round 2. Plug in 2, you get 20. Plug in 2, you get 16. Looks like 10x is taking it again. What happens in round 3? In round 3, you get 30. And over here, you get 81. Uh-oh. X to the fourth just took over. Round 4. In round 4, this you get 40. And I believe that's going to be like 256. What do you guys think is going to happen after this now? Do you think 10x is ever going to win? Or do you think that, oops, I wrote that last one wrong. Do you guys think that 10x will ever win again? Or do you think that x to the fourth is going to keep winning? The answer is x to the fourth is going to keep winning. Even though this guy started strong, it's because he had a big coefficient. But the thing is that even though this guy had a small coefficient, that power is much more powerful. So the bigger the exponent is, really the more powerful that particular term is. Okay? So why do I share that fact with you? Let's take a look at this polynomial. Which of these terms is the most powerful? The answer is this guy, right? So even though this guy's got a pretty big power and also a bigger coefficient, all of these have a smaller exponent, which means that really, as we keep going plugging in bigger and bigger values for x, it's this one that determines what happens with our function. This is the one that wins the game, the end game. And so if you want to know what the end behavior of a polynomial is, you don't need to pay attention to any of these. Because even though they'll definitely affect the polynomial in the beginning, this guy will drag him down a little bit because he's negative. This guy will pick him up a little bit because he's positive. This guy will drag him back down a little bit, and so on. And this negative 100 is really going to drop him in the beginning. But in the end, this guy determines what happens. And he's the one that says what happens as x gets bigger and bigger and bigger. So here's my point, is that the term with the biggest power is what determines the end behavior. Okay? The term with the biggest power is what determines the end behavior. All right, we're going to do the same thing we did in the last example, but now we're looking at a whole polynomial instead of just one term. So let's go ahead and take a look at this one. Number one, I believe this one's been printed for you, so you guys don't need to copy it. You can just fill in the blanks there. What can you conclude about the end behavior of this graph? Well, these guys might have some effect on the wibbling and wobbling of the function as it goes along, but ultimately at the ends, at the far extremes, this is the guy that determines what happens. So we just need to look at this. So what does this tell me about the end behavior of my function? Well, I have an odd power and a positive coefficient. When that happens, it's up on the right, down on the left. And we know how to write that in limit notation at this point, hopefully. Instead of writing the whole function, I'm just going to put y there, since y is equal to the whole function, right? Save myself some writing time. And as I move to the right, the limit of the function is positive infinity. So there you go. Let's take a look at number two. What can we conclude about this function? Well, notice that both ends are going down, and so they're going the same direction and going down. That means the coefficient is negative and the power is even. But the coefficient is negative and the power is even of what term? The first term. The term with the biggest power has a negative coefficient and a positive, an even power. So for instance, this thing could be something like this, a negative coefficient with an even power, and there could be anything in here. We don't know yet. We'll figure that kind of stuff out later. They could have all kinds of other stuff. It doesn't matter. What matters is this guy. So we know that the first term has to have a negative coefficient and an even power. All right, one more practice problem for you guys, just like that one. See if you guys can answer this, and that'll end our lesson. Okay, so here's our answers. First of all, since the leading term with the biggest power has a negative coefficient and an even power, it's down on the left and down on the right. So your arrow should look like this, and your limit notation should look like this. For number two, since it's up on the right, down on the left, opposite directions mean we have an odd exponent. Up on the left, down on the left, up on the right, down on the left means positive coefficient. So our first term, the leading term, has to have a positive coefficient and an odd exponent. And that's it, guys. So your homework will be posted for you guys, and have an enjoyable 3-day weekend.